In a purely resistive AC circuit, all of the energy delivered to the source is dissipated in the form of heat by the resistance. In a purely inductive AC circuit, all of the energy delivered by the source is stored by the inductor in its magnetic field during a portion of the voltage cycle, and then returned to the source during another portion of the cycle, so that there is no net energy conversion to heat. When there is both resistance and inductance, some of the energy is alternately stored and returned by the inductance, and some is dissipated by the resistance. The amount of energy converted to heat is determined by the relative values of the resistance and the inductive reactance. When the resistance is greater than the inductive reactance, more of the total energy delivered by the source is converted to heat by the resistance than is stored by the inductor. When the inductive reactance is greater than the resistance, more of the total energy is stored and returned than is converted to heat. The power dissipation in a resistance is called true power. The power in an inductor is reactive power and is expressed by the I squared R loss. Okay, so we've seen this before and when we talked about this in the purely capacitive circuit or the RC circuits. We have the same power triangle for the RL circuits. We have true power, we have reactive power, and we have the apparent power. And again, we make use of the right triangle to to display this and imagine it. So we have something called a power factor. Power factor is equal to the cosine of theta. As the phase angle between the applied voltage and the total current, the power factor decreases, indicating an increasingly reactive circuit. A smaller power factor indicates less true power and more reactive power. So let's look at an example here. Determine the power factor, the true power, and the reactive power, and the apparent power. So again, we've got a small series RL circuit. We've got both of our terms in ohms. We've got our reactive portion figured out. So we glean our values from the knowns. The impedance then is equal to 1K plus J 2K. We make our conversion into polar. So when we do our polar conversion here, we end up with Z in polar form 2.24 at an angle of 63.4 degrees in K ohms. Now we can use Ohm's law to determine the current in the circuit. We're given the source voltage as 10 volts. We have Z now 2.24 K ohms for the impedance, and we end up with a total current then in the circuit, this simple circuit, 4.46 milliamps. Since we know the angle, theta, 63.4, we can now calculate the power factor. The power factor is equal to the cosine of the angle. So cosine of 63.4 gives us a power factor of almost 1/2, 0.448 if we round it up. So now we can determine the true power, the reactive, and the apparent power. So the true power is the source times the current times the cosine of the angle theta. So when we calculate that, we end up with 20 milliwatts of true power. Now we can calculate the reactive power, the I squared R. So I squared X sub L is equal to 39.4 millivolt amps reactive. And then finally, the apparent power in volt amps is I squared Z, again another I squared R relationship, 4.46 milliamps squared, 2.24 K ohms gives us 44.6 milliamps of millivolt amps. So what's the significance of the power factor? Recall that the power factor is important in determining how much useful power, the true power, is transferred to the load. And in all of our circuits that we study, where we're interested in getting the maximum power to the load, this is an important calculation. The highest power factor is 1, or unity. A power factor of 1 indicates that all of the current to the load is in phase with the voltage, resistive. A power factor at the other end of the scale, 0, indicates all of the current is to the load, is 90 degrees out of phase with the voltage, and it's reactive. Generally, a power factor as close to 1 is possible is desirable. Think in terms of your speakers in your stereo. If you've got the greatest amount of power going to the load, your speakers are operating at maximum power transfer. A power factor almost equal to 1 indicates that most of the power transferred from the source to the load is the useful or true power. True power goes only one way, from the source to the load, and it performs work on the load in terms of energy dissipation. Reactive power simply goes back and forth between the source and the load, and there is no net work being done. Energy must be used in order for work to be done. Okay, we can look at an example here. Typical inductive load consisting effectively of inductance and resistance in parallel. We can see here what the meters are reading as the current is flowing, and we're determining how much energy is going to the load. Load with a relatively low power factor, 0.75. The load with the low power factor will draw more current from the source than a load with a higher power factor. The source must have a higher VA rating. The lines connecting the source to the load must be larger gauged wire. This condition becomes significant when very long transmission lines are required, as in power distribution. So we can see that power factor becomes very important in determining how much energy goes down your distribution lines for power to your neighborhoods and your commercial power. A typical inductive load consisting effectively of inductance and resistance in parallel. The load with a relatively high power factor, 0.95, so almost equal to 1. The load with the higher power factor will draw less current from the source than a load with a lower power factor. The source will have a lower volt amp rating. Both loads dissipate equal amounts of power as indicated by the power or watt meters. Thus, an equal amount of work is done on both loads. A higher power factor is an advantage then in delivering power effectively to the load. Power factor correction. When we come back, we'll take a look at power factor correction.